Welcome to The Explainer. Today, we are pulling back the curtain on a secret that literally holds our world together. From the tallest skyscrapers right down to the bridges you drive on every day.
You know, it's a secret that's hiding in plain sight, deep inside a material we all think of as the ultimate symbol of strength: concrete. And I promise you, once you understand this, you are never going to look at a city skyline the same way again.
So let's kick things off with concrete. It's everywhere. We trust it with our lives. But here's the thing. This seemingly indestructible material has a hidden flaw. A pretty surprising weakness, actually. Yeah, you can almost think of concrete as having a split personality. If you push on it or put it in what engineers call compression, it's an absolute beast. It can handle massive, massive loads without even breaking a sweat. But the second you try to stretch it or bend it, put it in tension, its other side comes out. It becomes brittle and it just snaps. And this isn't just a small difference. The numbers really tell the tale. According to the top authority on this stuff, the American Concrete Institute, concrete strength when you pull on it is only about 10 to 15% of its strength when you squeeze it. That one fact, right there, that huge imbalance, that's the whole problem that engineers had to solve. So that just leads to the obvious question, right? How in the world do we build these gigantic structures, these huge bridges and towers that have to flex and bend, using a material that basically shatters when you bend it? There has to be a trick. And that trick, well, it comes in the form of a partner. An unlikely partner, for sure. So let's bring in the hero of our story, steel. It's the other half of one of the most successful tag teams in the entire history of construction. Now, we're talking about a specific kind of steel, what we all call rebar. And listen, these are not just smooth metal rods. You see those patterned ribs all over them? Those bumps and ridges, the deformations? They are absolutely essential. They act like millions of tiny little anchors that let the steel grip the concrete from the inside. That grip is what makes the whole partnership work. And right here, this is why they are the perfect team. I mean, it is a textbook case of opposites attract. Concrete takes care of all the squeezing forces, and steel handles all the pulling and stretching. One material's critical weakness is the other's greatest strength. Put them together, and suddenly you have a brand new material with the best of both worlds. Okay, so we know they're a great team, but how does that partnership actually play out? You know, deep inside a concrete beam when it's really put to the test. The mechanics of it are actually incredibly cool and surprisingly elegant. All right, picture a load pushing down on a beam. As that beam starts to bend, the top gets squeezed together and the bottom gets stretched apart. At first, the whole beam, concrete and steel, is resisting. But as that load gets heavier, tiny, almost invisible cracks start to form at the bottom, right where the tension is highest. The concrete has hit its limit. It's failed. But, and this is the amazing part, at the exact instant it lets go, the steel rebar, which has just been waiting, instantly grabs that tensile force and holds the whole thing together. Now, this is the really wild, counterintuitive genius of the whole system. The steel isn't really doing much of anything until the concrete has already started to crack. The whole design is built around that one specific moment, a planned, graceful, and instantaneous handover of force, from the failing concrete to the waiting steel. That is the magic trick. Engineers have a pretty cool name for this perfectly balanced state. They call it the internal couple. What you've got is this immense pushing force in the concrete at the top of the beam, and it's being perfectly balanced by the immense pulling force in the steel at the bottom. This internal tug-of-war, this equilibrium, is what gives a reinforced concrete beam its unbelievable strength. Now, it's really important to get this. This partnership isn't some happy accident. Reinforced concrete isn't just concrete with some steel rods tossed in for good luck. No, it is a precisely, meticulously engineered material. Engineers don't just, cross their fingers and hope this all works out. They calculate every single detail to make absolutely sure that this handover of force is flawless, and that our buildings and bridges are safe. And when I say precise, I mean precise. They use these complex design tables, and this is just a simplified version, to get it exactly right. They're basically using data like this to figure out, for a very specific beam size under a specific load, exactly how much steel do we need.
You can see here how changing the ratio of steel, that R value, directly changes the beam's overall strength, the K value. And then they plug those values into formulas just like this one to calculate the absolute maximum strength of a beam. Now look, the goal here isn't for us to solve this equation. It's to appreciate the incredible level of scientific rigor that goes into making sure our world doesn't, fall down. So let's just zoom all the way out. Because this simple, elegant partnership between two totally different materials is basically responsible for the look, the feel, and the scale of our entire modern civilization. It truly is the hidden backbone of our world. Seriously, every time you drive over a bridge, walk into a skyscraper, fly out of an airport, or even just see a massive dam, you are looking at this principle in action. It is the super material that made the 20th century and everything in it possible. So let's wrap this all up. We started with concrete, right? It's amazing when you push it, but shockingly weak when you pull it. The genius solution was to embed its perfect partner, steel, which just so happens to love being pulled. This tag team creates a composite super material that's designed for that graceful handover we talked about. When the concrete finally cracks under tension, the steel is right there, ready to take the load. This balanced internal couple, all calculated with incredible precision, is the fundamental principle holding our world up.
Ultimately, the story of reinforced concrete really shows you the power of just incredibly smart design. This partnership didn't just change architecture. It literally built the modern world we live in today. And that leaves us with one last question to chew on. What new partnerships, what new materials will build the world of tomorrow? Thanks for joining us.